Hey everyone, ready for another deep dive?
Always ready.
Today, we're taking a crack at something pretty mind blowing, the hunt for brand new particles, the kind that could totally rewrite the physics textbooks.
Yeah, some new physics.
Exactly. And the really cool thing is, our source material is hot off the press, a scientific paper straight from CERN, the European Organization for Nuclear Research.
Home of the Large Hadron Collider.
That's the one. And get this paper was just published like last week, November 4th, 2024.
Wow, so it's really cutting edge stuff.
It is. So for anyone who might need a little refresher, what exactly does CERN do? I mean, it's this massive underground facility, but what's going on down there?
Well, they're basically smashing atoms together at ridiculously high speeds.
Like a demolition derby, but on a microscopic level,
Kind of, but the goal is to break those atoms apart and see what's inside.
like using a really powerful microscope.
Exactly. It's like if you wanted to understand how a watch works, you wouldn't just look at it from the outside. You want to take it apart, see all the tiny gears and springs, figure out how they fit together.
Makes sense.
And that's kind of what CERN is doing with atoms. They're smashing them apart to see what makes them tick, to see if there are even smaller, more fundamental pieces hiding inside.
So this is all about getting to the very bottom of things, the most basic building blocks of the universe.
You got it. And that brings us to the big question this paper tackles.
Mhm.
Are there undiscovered particles lurking in the subatomic world, particles we haven't even dreamed of yet?
Okay, now we're getting to the good stuff. So tell me, what exactly are these researchers looking for? What clues are they following?
They're on the hunt for something called a heavy resonance. Picture it as a brand new particle, something super heavy that decays really quickly into other particles we already know about.
Hmm. I'm trying to visualize this. So it's like a firework. The heavy resonance is that initial burst, and then it explodes into a shower of smaller sparks, which are the known particles.
That's a great analogy. And the researchers are particularly interested in seeing this heavy resonance decay into two very specific particles, the Z boson, the Higgs boson.
Ah, yes, the Higgs boson, the celebrity of the particle world. But can you remind me what exactly makes these two particles so special?
Well, both the Z and Higgs bosons are like VIPs in the standard model of particle physics. You can think of the standard model as our current best understanding of how the universe works at the most fundamental level.
Okay, so it's like the rule book of the universe.
Exactly. And the Z boson governs the weak force, one of the four fundamental forces of nature. It's involved in things like radioactive decay.
And without it, our sun wouldn't shine.
You got it. Now, the Higgs boson, well, it's responsible for giving mass to all other particles.
So if there were no Higgs boson, everything would be zipping around at the speed of light.
Exactly. No galaxies, no planets, no us.
Wow. Okay, that's kind of mind blowing.
It is. And that's why finding a new particle that decays into these two, the Z and the Higgs, would be a huge deal. It would be like discovering a whole new set of rules, a whole new chapter in the universe's rulebook.
New physics. So, how do these physicists even begin to look for something like this? They're dealing with these incredibly tiny particles smashing together at unimaginable speeds. It seems like finding a needle in a haystack.
You're telling me. It's incredibly complex, but that's where something called simplified models comes in. Think of it like a map or a guide to help narrow the search.
Okay, so it gives them a starting point.
Exactly. And in this case, they're using a model called the heavy vector triplet, or HVT model.
Catchy name.
Right.
Huh.
And this HVT model, it predicts the properties of these potential new particles,
Hmm.
how heavy they might be, how they might interact with the Z and Higgs bosons.
So, it's basically telling them where to look and what to look for.
Exactly. It's helping them navigate this incredibly complex world of particle physics.
Okay, I'm starting to get the picture. So they've got their target heavy resonance decaying into a Z and a Higgs. They've got their map, the HVT model. But this paper mentions they analyzed something like 138 inverse femtobarns of data. Can you translate that for us non-physicists? What does that actually mean?
Well, imagine you're trying to understand the population of a city by looking at a snapshot of a busy street corner. The more people in that snapshot, the more information you have. In particle physics, those people are collisions, and a femtobarn is like the size of that snapshot. Inverse femtobarns tell us how many of those snapshots we've taken and analyzed. So 138 inverse femtobarns. That's a mind-bogglingly huge amount of data, millions upon millions of collisions.
Okay, that's starting to sound less like a needle in a haystack and more like a needle in a mountain range.
Hmm.
So how do they even begin to sift through all that data? I mean, they must be using some seriously powerful tools, right?
They are. And here's where it gets really cool. They're using machine learning.
Oh, wow. Like the same technology that powers our social media feeds and streaming services.
The very same. But in this case, they're using it to train algorithms to spot specific patterns in the data, the patterns that could indicate a new particle.
So, how do they teach a computer to recognize a new particle? I mean, something that's never been seen before.
It's all about training data. They feed the algorithm simulated data, showing it what the decay of a heavy resonance should look like based on their models.
So, it's like giving the computer a set of fingerprints to look for in a massive database.
Exactly. And these collisions, they produce these incredibly complex sprays of particles called large radius jets.
Jets.
Yeah, imagine like a fireworks display.
Mm.
The initial explosion is the collision, and then you have these jets of particles spraying outwards.
Okay, so it's a very chaotic, very explosive scene.
It is. And the machine learning helps them analyze these jets, sift through all that chaos, and pick out the patterns that might point to a new particle.
So the computer is scanning these collisions, looking for that specific fingerprint, the one they trained it on.
Precisely. But here's the thing. There's a lot of noise in the data, a lot of random fluctuations that could potentially fool the algorithm.
So how do they make sure they're not chasing after false positives?
That's where a special tool called the HBSQ-CD discriminant comes in. Think of it as a filter that helps separate potential signals of new physics, the background noise.
Okay, break that down for me. HVSQCD.
So QCD stands for quantum chromodynamics. It's the theory that describes the strong force which is responsible for holding quarks together inside protons and neutrons. The H stands for Higgs. So this discriminant helps tell the difference between events where the Higgs boson might be playing a role and the more common events driven by the strong force.
Okay, so it's like separating the wheat from the chaff, helping them zero in on the events that are most likely to reveal something new.
Exactly. But even with these powerful tools, finding a new particle is incredibly challenging. It's not enough to just find any pattern they need to find specific patterns that match the predictions of their models.
So it's like having a map, but then needing to carefully examine each landmark, each twist and turn to make sure it's really leading you to the treasure.
That's a great way to put it. They're not just looking for any bump in the data. They're looking for bumps that are in the right place, have the right shape and fit with everything else they know about particle physics.
So how do they actually go about testing those predictions? What are they specifically looking for in the data to tell them whether they've found a new particle or not?
Well, they focus on specific ways the Z and Higgs bosons might decay. Each decay pathway leaves a distinct trace in the detector, a kind of signature.
Like a fingerprint?
Exactly. And they're looking at different channels,
Hmm.
which basically means different combinations of decay products. For example, they're looking for cases where the Z boson decays into a pair of electrons or a pair of muons or even invisible neutrinos.
Okay, so they're looking at all these different possibilities, all these different ways the Z and Higgs bosons could break apart.
Right. They're also looking for the Higgs boson decaying into different types of quarks, which are the even tinier particles that make up protons and neutrons.
Wow, so many possibilities. It's like trying to solve a puzzle with a million different pieces.
It is. But that's the beauty of particle physics. It's all about piecing together these tiny clues, these fleeting traces of particles to unlock the secrets of the universe.
So how do they know if they've found a real piece of the puzzle or just a random bit of noise? I mean, how do they distinguish between a genuine signal and just a statistical fluke?
Well, that's the million-dollar question, isn't it? It all comes down to statistical significance. They analyze the data looking for bumps, little excesses of events that stand out from the expected background. It's like looking at a graph and seeing a little peak where you wouldn't expect one.
Okay, so if they see a bump in a specific region, that could indicate a new particle.
Exactly. But here's the thing. That bump needs to be statistically significant. They have to be really, really sure it's not just a random fluctuation. Think of it like flipping a coin. If you flip it 10 times and get heads 8 times, you might think, something's up.
Ah.
But it could just be luck. If you flip it 100 times and get heads 80 times, well, then you might start to suspect a loaded coin.
So it's all about the probability of that bump appearing just by chance.
Right. And particle physicists are incredibly cautious. They need to be really sure before they claim a discovery. So they use something called confidence levels to express how certain they are about their results.
So it's not just about finding a bump, it's about making sure that bump is the real deal. So drum roll, please. Did they find anything? Did this paper reveal a brand new particle?
Well, in this specific case, they didn't find conclusive evidence for the heavy resonance they were searching for.
Oh, so no Nobel Prize this time.
Not this time. But that doesn't mean this research wasn't valuable. Even though they didn't find the particle, they were able to rule out certain possibilities. They were able to say, okay, if this particle exists, it can't be within this range of masses.
So it's like narrowing down the search area, eliminating some of the hiding places.
Precisely. And they also learned more about the HVT model itself. By comparing their results with the model's predictions, they were able to fine-tune some of the parameters, like they're refining their map, getting a better understanding of the terrain.
The hunt continues. Where do they go from here? What are some of the next steps in this grand search for new physics?
Well, one approach is simply to collect more data. The more collisions they analyze, the more sensitive their searches become. It's like using a stronger magnifying glass to see those tiny details.
Makes sense. And I imagine technology plays a big role too. Are there new tools or techniques on the horizon that could revolutionize this field?
Absolutely. One of the most exciting prospects is the development of new types of colliders. Right now, the Large Hadron Collider is the most powerful collider in the world, but there are ideas for even more powerful machines like muon colliders.
Muon colliders, those sound intense.
They are. Imagine a collider like the LHC, but instead of colliding protons, which are made up of quarks, it collides muons. Muons are fundamental particles, like electrons, but much heavier. And this allows them to reach much higher energies, potentially unlocking a whole new realm of particle physics.
Wow. So it's like upgrading from a bicycle to a rocket ship in terms of exploration potential.
That's a great way to put it. And aside from more data and new technologies, there are also different ways to approach the search itself. This particular paper focused on what they call non-VBF production. But another exciting avenue is looking at VBF, which stands for vector boson fusion. It's a different way to produce those heavy resonances inside a collider.
Okay, you've piqued my curiosity. What's so special about VBF? What makes it different?
In VBF, the heavy resonance is produced through the interaction of two force-carrying particles, like W or Z bosons. Think of it like this. Instead of the protons themselves colliding head-on, they sort of swing these bosons at each other, and those bosons then collide to potentially create the new particle.
So it's like a billiard shot where the bosons are the cue ball and the heavy resonance is the target ball.
That's a perfect analogy. And what makes VBF so interesting is that it produces a very distinctive signature in the detector. The signal is much cleaner, easier to separate from the background noise. It's like trying to hear a conversation in a crowded room versus having that same conversation in a quiet library.
Ah, so it's like having a spotlight on the action, making it easier to see what's happening.
Exactly. And because VBF involves the weak force, which is governed by the Z boson, it's particularly sensitive to new particles that also interact via the weak force. It's like having a specialized tool for probing a very specific aspect of the subatomic world.
So by exploring both non-VBF and VBF production, physicists are casting a wider net, increasing their chances of finding something truly new and groundbreaking.
Exactly. And that brings us to an interesting point. This paper focused on non-VBF production. But VBF itself could be a very promising avenue for future research, especially when it comes to hunting for these heavy resonances.
Okay. You're definitely leaving me wanting to know more about this VBF thing. Why is it so promising? What makes it such a potentially powerful tool for uncovering the secrets of these hidden particles?
Well, it has to do with the unique way VBF events unfold inside the detector. Remember how I mentioned that in VBF, the heavy resonance is produced through the interaction of two force-carrying particles, like the W or Z bosons?
Yeah, like those bosons are playing a game of subatomic billiards using the new particle as their target.
That's the idea. And what makes VBF so interesting is that it tends to produce a very clean signal in the detectors. You see two jets of particles that are very far apart, and there's very little other activity in the central region.
So it's like a spotlight shining right on the action, making it easier to see what's happening.
Exactly. And that makes it easier to separate the signal of a potential new particle from all the background noise, from all the other processes happening in the collision.
Okay, that makes sense. Less clutter means a better chance of spotting something truly unique. But you also mentioned something else, that VBF is especially good at finding particles that interact via the weak force. Why is that?
Remember, VBF involves the exchange of W or Z bosons, and those are the very particles that carry the weak force. So it's like using a fishing rod designed specifically to catch a certain type of fish. If those heavy resonances also interact via the weak force, they're more likely to show up in these VBF events.
So it's a way to really target the search and increase the chances of finding those specific kinds of particles.
Exactly. It's a powerful tool. And what's even more exciting is that we're really just starting to explore the full potential of VBF. As we gather more data and develop better analysis techniques, Who knows what we might find?
It's pretty mind-blowing to think about. So even though this paper didn't find the specific heavy resonance they were looking for, it feels like the journey's just beginning.
Oh, definitely. Every experiment, whether it leads to a new discovery or not, it adds to our knowledge and helps guide us toward a deeper understanding of the universe.
Well, I have to say, this has been a really fascinating deep dive. Thanks for taking the time to break it all down for us.
My pleasure. Always happy to talk about particle physics.
And who knows, maybe one of our listeners will be the one to make the next big breakthrough in this field. Until then, keep those brains buzzing and never stop questioning the universe. Thanks for tuning in, and we'll catch you on the next deep dive.